The purpose of the classes on recursion is to get you extremely comfortable with recursion, because this is something that you can really not let go of. If you become great at recursion, then you become great at backtracking, and if you do that, then topics like DP automatically becomes very, very easy for you. Okay, so let us start. So basically, all of you might be already aware of something like a function. Okay, so by function I mean any user defined function. So you define a function that takes in something and returns something. Okay, now basically what happens that any function needs to be invoked from some outside area. Okay, and that outside area might be main. So it could be that from main you are invoking this func of 5 or whatsoever. Okay, so the thing to understand over here is that whenever a function calls other function, then there is a control transfer that happens from here to here. And I had already spoken about this when I was talking about time and space complexity, that whenever there is a control transfer from one function to the other function, a stack is getting created. How many of you remember that? The call stack that gets created whenever there is transfer of control. So this is the first thing that all of you should keep in your mind, that your program anyways starts from main. So it would be like the main function is currently in your call stack. Now at this point of time, func of something has been called, so this func will now come at the top of the stack. And now when this has returned something or this has exited, then this will be popped off and the control will come back to the main, and main will start executing after this. Okay, so this is how the things happen. Now this was a normal function call. This was just a normal function call. This was not recursive function call. But the point to understand over here is whenever inter-function calls happen, that is when a function calls other function, then there is a caller function and then there is a called function. So main is the caller and func is the function that has been called. Okay, now when it calls, it can pass some parameter. Okay, and that parameter is passed to the function that has been called, and if it returns something, then whatsoever it returns gets returned to the parent. Okay, so see, these are very, very simple things, but when you see any advanced problem on recursion, you forget these things. Okay, that is the reason you feel hazy over there. So keep this very, very clearly in your mind, that there is a caller, so there is a parent. So like main is a parent of func. Okay, and main passed 5 to the func, and this func returned something like 0 to the main. Okay, so these are the things that you should be very clear about: the calling function and the called function, and what are the values passed and what are the values that are returned. Okay, now, so basically what happens, what is recursion now? Recursion is nothing but a function calling itself over and over again with different parameters or inputs. So recursion means that the same function will call itself again and again with different inputs. Okay, now a classical example of this could be, as I had shown you, computing factorial of a number. Okay, so when you compute factorial of a number, you already see that n factorial is n multiplied by n minus 1 factorial. So a function that calculates factorial of n can be written as n multiplied by factorial of n minus 1. So this function can call itself again with a different value of parameter. Okay, and this is how the code can be written. Now, few things that all of us should keep in our mind are, there are 3 principles of recursion, and if you very stringently ensure that these three principles are being written in your code, then there is very less likelihood that you will make an error. Okay, now let us talk about those principles. First principle is initialization, second is recurrence relation, and the third one is termination condition. So I'll talk about each of these through an example. So let us all see that. What do all of these mean? So let us say I am writing a code for factorial. So this is int factorial int n. This thing that relates a larger problem to a smaller problem, this thing is called as recurrence relation. Okay, so this is done. This is my recurrence relation. Now the most important thing that people forget is that recurrence relation is not true for all the inputs. It is not true for all the value of inputs. Do you get what I'm trying to say over here? Fact of n equals to n into fact of n minus 1 is not true for all the inputs. For which input this is not true? If I put n equals to 0, will it be true? No. For n equals to 0, you cannot write fact of 0 is 0 into something, because that will be 0. Because factorial of 0 is what? It is 1. So the case where this thing is not true, that case is called as termination condition. And that being the reason, first line of code must always be termination condition. Because if you don't write termination condition first and you write something else, then what will happen? Your code will never terminate. It will keep calling itself over and over again by changing the parameters for illegal values also. So always first write the termination condition, which is your edge case, which is something that doesn't abide this equation. So what will be my termination condition? If n is equals to 0, that means I am trying to calculate factorial of 0. So what should I return? 1. Otherwise, what should I do? I should simply return n multiplied by fact of n minus 1. Okay, so this is my code for factorial. The first thing that you are seeing over here is termination condition. The second thing that you are seeing over here is recurrence relation. And now what about initialization? Initialization is the first call made to this function from any outward function. Because this is a recursive code. Now for recursion to get triggered, there has to be a trigger point, and that trigger point will be a call from outward function. Okay, so if there is an outward function main that for the first time calls func of 5, this thing is called as initialization. So these are the three things. Initialization means the first call. Recurrence relation means the most important thing that relates a problem of larger size to a problem of smaller size, and termination condition is the thing that doesn't abide by the recurrence relation. So whenever you are, before you pick up your pen or pick up your keyboard to start writing the code, ensure that you are very, very clear with all these three things. If you're not very, very clear with all these three things, chances are that you might make an error. Okay, Vaibhav is asking if func A calls B, B calls C, and C calls A, will that also be a recursion? No, this will not be recursion. See, in general, recursion is same function calling itself over and over again. Okay. Cool. So let's go ahead from here. Now see, although this code is very simple, but we'll just try to, understand the few things that I have just written over here, that there is a calling function and then there is a called function. So I'll draw some very simple diagram, but there is a very strong message that I am trying to convey from here. And the same message I'll be conveying for the next 2 classes also. So you better get it very concretely. So see, how will the execution happen? Let us go by the execution. First, there is a main function. Okay, so there is a main function. This main function invoked func of 5. So let me do that. This invoked func of 5. Now, when func of 5 is called, so the control has come over here. If condition will not be true for n equals to 5, so this line of code will be executed, and this is saying that this would return n, which is 5 multiplied by fact of 4. So again, this will now call func of 4. Okay, I am writing func, this is fact by the way, so please don't get confused. Okay, so now the thing to understand over here is until unless func of 4 returns something to func of 5, this func of 5 cannot multiply that with 5 and return it to main. Are you getting what I am trying to say? So if there is a call from parent to child, parent has to wait for the child to get over or to return something, and now when it returns something, then it can use that thing to multiply it to something and now return it to its parent. Okay, cool. Now func of 4, so when n is equals to 4, now it will call func of 3. The same logic I want to speak over here also, that for func of 4 you want to return 4 multiplied by func of 3. Now until unless func of 3 returns you something, you cannot multiply that with 4 and return it to your parent. Okay, so it will wait silently. Similarly, func of 3 will call func of 2, func of 2 will call func of 1, func of 1 will call func of 0. Now see, when I have reached func of 0, so my n is equals to 0 and this is my termination condition. Okay, so this is my termination condition. So what would happen? This func of 0 would immediately return a value 1. To whom will it return? It will return 1 to its parent, which is func of 1. Now what will func of 1 do? When func of 1 was called, it tried to return 1 multiplied by func of 0. Func of 0 is 1, so now it will multiply 1 with 1 and return that to its parent. Okay, now func of 2, it has got the output from its child, so it will multiply this thing with 2 and return it to its parent. Now func of 3, it has got outputs from func of 2, so it will multiply 3 with this thing and return it to its parent. Same thing at here, func of 4 has got output from its child, so it will multiply 4 with this entire thing and return it to its parent. And the same thing over here, that func of 5 has got output from func of 4, so it will multiply 5 with this entire thing and return it to the main function. So this is how the thing happens over here, and the only important thing that I had to know here was that every call, every pair of call or every consecutive pair of call that you see can be modeled as parent and a child. Parent calls child, and whatever child returns, that is returned to the parent. And the same thing that happened over here would happen over here also, that this child will return to its parent. Okay, so the most important thing to see over here is that function call propagated from top till bottom, but the returns happened from bottom till top. Okay, this is the reason recursion works. Another thing to say here would be that this is a very important key player, because until unless you return the right value from bottom, if you return some gibberish value, some garbage value from here, all the values that are getting returned would be polluted. Okay, so this is also very, very important, that your termination condition is bang on. Okay, the same thing that I have done over here, this is also called as recursion tree diagram, and by recursion tree diagram I mean to say that how every function is like a node. So main is like root. Okay, main is like a root node, and it has a child which is this, it has a child which is this, and so on and on and on. So here every parent has just one child, because every function was calling just one instance of itself, but it might not always be the case. So if you have done pre-order traversal or in-order traversal on trees, you might have seen that a function, recursive function, calls 2 or more instances of itself. Okay, so in that case you will have many branches emerging out. Okay, yeah, even in Fibonacci. So we will be seeing one such example over here. One more thing, that this entire thing is like a stack only. So this main would be at the bottom of the stack, and this func of 0 would be at the top of the stack. What will be the stack size? What will be the size of stack if the number whose Fibonacci value is to be calculated, the number whose factorial is to be calculated is n. It will be order n plus n, including main function also, and like I can very specifically say that as order of n. So order of n will be the extra space required over here, and that extra space would be the recursion stack size. Okay, one more thing that you should understand over here is how do I comment on the time complexity. So what will be the time complexity? I'm sure all of you will say order n, but anyone who can be more precise. So the way to see that easily could be something like this, that see, first there is a control flow that happens from top till bottom. So this control flow that happens from top till bottom will take order n time, and now when return happens, then at each level there is just order 1 multiplication. There is just one multiplication that happens. So again here when it returns back, there is just order 1 operation happening, order n calls, order n operations would happen. So overall it would be n plus n, which is 2 into n. Okay, so another way to visualize it could be that you have a stack, and in that stack you inserted all these things, okay, when you were going from here to here, and while coming from here to here you popped all those things. So inserting n elements and then popping all those n elements will take how much of time? 2 into n, to be very, very precise. So that is the total number of operations that will happen over here. You can understand it this way. Okay, now the stack is very, very evident. I had spoken it before also, that if recursion is to be implemented, then because of this thing that control goes from top to bottom and eliminates from bottom till top, I have to use stack. I cannot use anything else for this. Okay, cool. One more thing, here the code was recursive, but don't you think that I can calculate factorial of a number using iterative code also? I think I can do that, right? Without recursion also I can get that calculated. In that case, why do we use stack? Because see, the thing over here is that the call that has propagated from top till bottom. So the first element to be inserted was main, and the last element to be inserted was func of 0. But the first element to be popped was func of 0. So whatever was last in, that is first out. Did you get it now? That is the reason, because of this last in first out nature of recursive function calls, I must use stack. Yeah, so this is how recursion works. Another thing that all of you should understand over here is that I spoke about recursion tree that I might want to draw and see how things happen. But before that, one more thing, I can write iterative code also. Yeah, so if I write the iterative code for this, then there will not be any extra space. Do you all see that? If I write the iterative code for this thing, there will not be any extra space, but the time complexity will remain the same. So I can clearly say that if I have to find factorial of a number, instead of using a recursive approach, I must always go for something like iterative approach, because iterative approach takes the same time but doesn't consume any extra space. So these are the, now depending on the problem, it happens that you have to decide whether iterative approach is better or recursive approach is better, which we'll investigate later on. But please keep it in your mind that recursion takes the space, and the space is nothing but at any point of time what was the maximum size of your stack. And why did I use this word at any point of time? Why did I use this word? Because this stack is dynamic, this is changing. Okay, its size initially was 0, then it became 1, then 2, then 3, and then it started popping. So at any instant of time, whatever was the maximum size, that would be the maximum space consumed. So let us go ahead. Now what we'll do is, I'll give you a code snippet. Okay, you will have to take a look at that code snippet and tell me the output of that. Okay, so that is the first thing that we are going to do, and that will give me an idea that how many of you are clear to some extent with how recursion works. Okay, so let us take a look at one code. So there is a code void func. Void means it will not return anything. So let's say it takes integer x. Okay. So first thing that it does is it prints the x, and then it sees that if x is greater than equals to 3, then it simply returns semicolon. You know, although this is a non-returning function, but I can write this statement over here because this just means exit. This is as good as exit. So it will not return anything to its parent, it will simply exit. That is, this function call will be popped from the stack of function calls. Okay. Okay. After this I have 2 more lines of code, func of x plus 1 and then func of x plus 2. Okay, and let's say my main function was over here, and from main I invoked func of 0. So just take a look at this code, and can you see the 3 things over here? Can you see the 3 principles of recursion? Are they present over here or not? Initialization, termination condition, and recurrence relation. So where is the initialization? This line, which is the first call to this function. Okay, and then where is the termination condition? This is the termination condition. Okay, and these 2 are the recurrence relations. Okay, so take a look at this and then tell me what will be the output of this code. First call is for func of 0. Use your pen and paper. Do not gaze silently, but use your pen and paper and then do some work and tell me what will be the output of this code. Okay, so you can send your responses publicly instead of sending it privately to me. So Priyam, I saw your answer, but I believe that is not right. Think again. Okay, so 2 of you are saying that the output would be 0, 1, 2. Anyone who is getting a different output? 0, 1, 2, 3. 3, 4. One of you is saying infinite loop. Okay, so I can see that there are different answers that you guys are saying, and you can also see that the variety of answers that is coming. The reason is that maybe some of us are not very clear with the way recursion works, because I believe this is not as easy as factorial. So in factorial there was just one branch, here there are multiple branches. So just concentrate on the board for 5 minutes, and after those 5 minutes you can handle any recursive code, and I can guarantee that. So this is the foolproof way to investigate any recursive code through a popular technique called as recursion tree diagram. Okay, so I'll draw a recursion tree diagram, and that will make things crystal clear for you to understand. So stop doing whatsoever you are doing and just look at the board. See, first call that has been made is for func of 0. So I'll first create the root node as f of 0. Okay, this is very easy to understand. Now let us start executing f of 0. Okay, let us start executing f of 0. So what is the first thing that f of 0 does? What is the first thing that f of 0 does? It simply prints the value which is 0. So the first thing that it will do is it will print 0. Okay, now this if condition will not be true for 0, so I will come down. Now this f of 0 will call f of 1 and f of 2. Now do you understand one thing, that until unless f of 1 is completely over, f of 2 will not begin. Do you see this thing very clearly? Until unless f of 1 is completely over, f of 2 will not begin. So let us somehow model that pictorially over here so that we don't confuse our brain. Okay, so f of 0 will invoke f of 1 and will wait for some time. So f of 2 has to wait for f of 1. So until unless this completely explodes and gets done, this will not kick in. Okay, now I am at f of 1. Now see, this is the beauty of recursion, that the thing that happened at this node will happen at this node also and will happen at this node also. So now f of 1 will start executing and f of 2 is waiting for that. Okay, so for f of 1, what is it that is going to happen? First it will print the value that is 1. Okay, now this condition is true for 1, sorry, this condition is false for 1. So what will happen? It will come down and it will invoke f of 2 and f of 3. Now again, do you see this thing here also, that this f of 2 will be executed first and then this f of 3 will be executed? Do you see this thing over here as well? So leftmost thing is the first thing that is done, rightmost thing is the thing that will be done in the end for every node. Okay, similarly now for f of 1, it will first print 1, then it will call f of 2 and then f of 3. Now do you see one thing, that this f of 2 which was just waiting for f of 1, now it will wait for this also and this also. Do you see that over here? F of 2 will now wait for both this f of 2 as well as this f of 3. So this is what is last in first out principle. Okay, the function which is last in, okay, which just came in, will execute first and this will have to wait. Okay, so let us keep doing the same thing again and again. Now I am at f of 2. Okay, so first f of 2 will be executed, so it will first print the value 2 and then it will invoke f of 3 and then it would invoke f of 4. Now when I am at f of 3, what will happen? Tell me. For f of 3, it will first print the value 3. Now this if condition, will it be true for f of 3? Will it be true for f of 3? Yes. So what will happen? That this function will exit. This function will exit. So f of 3 will essentially exit. Now f of 3 exits, what will happen? Control will transfer back to whom? To the parent. This is very important thing. Whenever a child exits, the control transfers to whom? Control transfers to the parent. And now the parent would call f of 4. Is that clear to everyone what I am trying to say over here? So essentially after f of 3, f of 4 will be executed. Now f of 4, what will it do? It will first print the value 4 and now this condition will be true, so now this will also exit. Now this has exited, so the control will transfer to whom? Control will transfer to f of 2, which is the parent. Now this f of 2 is also entirely over, so the control will transfer to its parent, okay, which will now invoke f of 3, right? Now f of 3, what will it do? It will first print the value which is 3 and then based on this if condition, it will simply exit. Okay, now what happens? The control transfer here, f of 1 is completely over, so the control transfers over here and now f of 0 invokes this. So did you see this thing coming true, that once this f of 1 has completely exploded, then only the control reached over here? Can you relate that thing over here? Now if you see clearly, the way this f of 2 is going to create its jungle over here is exactly how this f of 2 created, isn't it? What is the difference between this f of 2 and that f of 2? Nothing. F of 2 got called here also and it was called over here also. So the same logic, applying the same logic over here, when f of 2 has been called, it will first print the value, that is 2. Okay. Now this condition is not true for 2. So what will it do? It will invoke f of 3 and then it would invoke f of 4. So f of 3 will first execute and then f of 4. What will f of 3 do? It will print the value 3 and based on this if condition it will simply exit. So control will now go over here, it will print 4 and then exit. Now the entire thing has got exited. So this is how you can model your recursive code as a tree. So now predicting the output becomes very easy. The first thing to be printed was 0, then 1, then 2, then 3, then 4, then 3, then 2, then 3 and then 4. So the output is 0, 1, 2, 3, 4, 3, 2, 3, 4. This is how the output has got created. So this is how you can inspect any recursive code and you can predict the output very easily. So see, this is a technique which is very fast and using this you can predict the outputs. But now we will understand that how exactly is this code executed on your system. So will you please make recursive stack for the, yeah, we'll do that. So the thing to understand over here is that, do you see this thing clearly, that this thing will be executed by your system in form of a stack. So now I will basically be creating a stack wherein you will completely understand that how stack implements this code on your behalf. One more thing, looking at this tree, can you tell me the maximum stack size? What would be the maximum stack size? Can you conclude from this tree? It will be nothing but it will be the longest path from root to any leaf. And what is the longest path from root to any leaf? That is almost 4. Okay. So because this longest path will actually correspond to the maximum number of functions that will be waiting for each other in a stack. Okay. And now when I draw the stack, you will see the exact same thing. So let us just draw that stack. So just look at here. So the stack of system calls that I have, stack of function calls, sorry, that I have, it contains two things. First thing is the function call that has been made. So the first function call that has been made is f of 0. And now let me split these things as separate instructions. Let me call that this is instruction number 1. This is instruction number 1, and then this print was my instruction 1. This if condition was my instruction 2. This was instruction 3 and this was instruction 4. So the reason I have written down these is because I need to keep a track of this fact that which function call has executed how many instructions. And how many of you can relate to it, that why is it essential? Why do I need to know that? Which function call has executed how many instructions? So we'll see that if you can't relate to it right away. So initially f of 0 has been called. How many instructions has been executed? For f of 0, how many instructions have been executed as of now? 0 instructions, right? 0 instructions. Why are you saying 3? This is the first call. Until now no instructions have been executed. So to start with, f of 0 has been pushed into the stack and 0 instructions has been executed. Now let's go ahead. Okay. Now when f of 0 has been called, the first thing that will happen will be to print the value 0. So 0 will get printed over here. Now it will come to this if condition. If condition is false, so it will move down. And now what happens? It sees that there is a f of 1. So f of 1 will get called. What do I mean by f of 1 getting called? F of 1 getting called means that f of 1 will be pushed on the top of my stack. So above f of 0 you will have f of 1. Now can you tell me how many instructions of f of 0 have been executed? By the time f of 1 is pushed, how many instructions have been executed? Why 2? This is 3, right? 3 instructions have been executed. 3, 3, 3. F of 0, printing happened, if condition was evaluated, this function call has been made. So 3 instructions have been executed for this. And since this has just been pushed, so 0 instructions have been executed. Are you able to understand how 3 instructions have been executed? Number of instructions is simply the number of lines of code that have been executed basically. Okay. Now, you know the nature of stack. Like when your system executes a recursive code using a stack, it just has access to the top of the stack. So now at the top of the stack you have f of 1. So it will start executing f of 1, and from where? From the first instruction itself. So what will happen for f of 1? The first thing that will happen is print of 1. So 1 will be printed. This condition is false for 1. Now f of 1 will call f of 2. So what will happen, that I will get f of 2 at the top of the stack, below which I have f of 1 and below which I have f of 0. So for f of 0, 3 instructions were executed. For f of 1, how many instructions have got executed? 3. Again 3, right? So for f of 1 also 3 instructions got executed, and f of 2 is at the top with 0 instructions. Now f of 2 will execute. So for f of 2 also, first thing that will happen is to print the value 2. So first 2 will get printed. Okay. Now this condition is false, so it comes down. F of 3, it will invoke f of 3. So now what is going to happen is that you have f of 0, f of 1, f of 2 and f of 3. So for f of 0, 3 instructions, f of 1, 3 instructions. For f of 2, how many instructions have been executed? For f of 2 also 3 instructions have been executed, and at the top I have f of 3, for which 0 instructions have been executed. For f of 3, what will happen first? For f of 3 again, first it will print the value that is 3. Now, is this condition true for f of 3? Is the if condition true for f of 3? Yes, if condition is true for f of 3. So what will happen? Tell me. Return. What does the return mean? Return means that f of 3 will exit. F of 3 will exit, that means f of 3 will be popped from the stack. So f of 3 will be popped from the stack, and now what will I have is f of 0, f of 1, f of 2 all have executed 3, 3, 3 each. Now the control transfers back to the parent. You see how the control transfers back to the parent when child has exited, how the control transfers, and you can relate from here why stack is being used. Okay. Now the most important thing, do you understand the significance of this thing now? Do you understand the significance of this thing, that till what line number I have executed? Because once system sees that the top of my stack is f of 2, system needs to know that from where do I need to run it. Because if this information is not present, it will start executing f of 2 from line number 1 again. How many of you are getting that, what I am trying to say? So basically system needs to know that when control transfers back to a function, how many instructions of this function were already executed, so that I don't have to reinvent the wheel again. Now I am at f of 2. 3 instructions have already been executed. So from where will it start? From where will it start? It will start from instruction 4. So what will it do? It will push f of 2 plus 2, which is f of 4. So at the top of my stack, I will now have f of 4, below which I have f of 2, below which f of 1, and then f of 0. They had 3 instructions executed. Now how many instructions have been executed for f of 2? 4 instructions. So now for f of 2, all the 4 instructions have been executed. And at the top of the stack, I have got f of 4, for which 0 instructions are executed. Now for f of 4, first thing that will happen is to print out the value 4. Okay. Now this condition is true for 4. So what will happen? It will return. Return means f of 4 will be popped. So if f of 4 is popped, what will happen? I will have f of 0, f of 1, f of 2, 3 instructions, 3 instructions and 4 instructions. Now whatever is the top of my stack, all the instructions have been executed for it. Do you see that? Whatever is the top of my stack, for that all the 4 instructions are already executed. So what should happen? What should happen? It will be popped. So do you see there are 2 conditions in which your system pops the top element from the stack. First condition is that the current instruction for that is to return or to exit. Or the second condition is that all the instructions have been executed and nothing is left. No line of code is left. So how many of you are trying to understand that, what I just spoke? So this is the most important thing. So now what will happen, that f of 2 would be popped. So if f of 2 is popped, what will happen? I have f of 0, I have f of 1, 3 instructions for all of them are executed. Now I am back to f of 1, and for f of 1, 3 instructions are executed. So what will happen now? What will happen now? Everything happens automatic. All these things are being taken care of by your system. You don't do it, right? So now f of 1, 3 instructions are executed. So fourth instruction is to call func of 1 plus 2, which is f of 3. So it will now push f of 3 with 0 instructions executed. And now for f of 1, all the 4 instructions are executed. And for f of 0, 3 instructions were executed. Now the top of my stack is f of 3. So what would happen? Top of my stack is f of 3. So what would happen? It would first print the value 3. Why pop? F of 3, 0 instructions are executed. So it will start from instruction number 1. And what is it that it will do first? It will first print the value that is 3. And now this if condition will be true. If this if condition is true, so return would happen. Return essentially means that f of 3 will be popped. So if f of 3 is popped, I'll have f of 0 and f of 1 with 3 instructions and 4 instructions. Now again you see that for f of 1, all the 4 instructions are executed, isn't it? For f of 1, all the 4 instructions are executed. So what will happen? F of 1 will be popped from the stack. Okay. So now f of 1 gets popped, and now I have f of 0 with 3 instructions executed. Okay. Now what will happen? F of 0, for f of 0, 3 instructions were executed, right? For f of 0, 3 instructions were executed, and then everything came above it. Now when I come back to f of 0, I see that, hey, 3 instructions were already executed. So I'll start with 4th instruction. And what is 4th instruction? It is to push f of 0 plus 2. So what will happen? F of 2 will come to the top with 0 instructions executed. And now for f of 0, how many instructions have been executed? How many instructions have been executed for f of 0 now? All the 4 instructions, right? Now again, for f of 2, what will happen? It will start from first instruction. So first it will print this value 2, and this condition will be false. So now it will push f of 3. So I will get f of 3 at the top, below which I have f of 2, and here f of 0. For f of 2, how many instructions got executed? Printing happened, if check happened, and f of 3 push happened. So how many instructions got executed? 3 instructions, right? So for f of 2, 3 instructions are executed, and f of 3 is at instruction number 0. So for f of 3, first I'll print the value 3, and then based on this if check, I'll pop this. So now I have f of 0 with 4 instructions and f of 2 with 3 instructions. Now I am at f of 2. For f of 2, 3 instructions are executed. So now what will happen? 4th instruction will execute. And what is 4th instruction? What is 4th instruction? 4th instruction is to push f of 2 plus 2, which is f of 4. So at the top, now I will get f of 4 with 0 instructions executed. Below this I have f of 2 with all the 4 instructions executed, and below this I have f of 0 with all the 4 instructions executed. F of 4, it will first print the value that is 4. Based on this if check, it will pop this Now I have f of 0, f of 2, all 4 instructions executed. Eventually what will happen? F of 2, everything is done, it will be popped. Then f of 0, everything is done, it will also be popped, and eventually your stack will be empty. So do you see that I started my journey with an empty stack and I ended also with an empty stack? How many of you understood these steps clearly, that how recursion has been implemented using a system stack? So this is how the things actually happens, okay? You maintain a stack of functions that are waiting for each other to get executed, and you also need to remember this fact that for the last function, how many lines were executed, so that you can start from the next line rather than starting from the first line, okay? Now again, if you see over here, what is the maximum size of stack at any point of time? The maximum size of stack at any point of time is just 4, which was the same in the previous case also. And this stack is dynamic. At different points of time, it has got different sizes. So the maximum stack size would be order of 4. Okay, cool. So I believe you can very clearly relate, given a particular question, that how recursion is coming handy over here, and how basically the recursive code is getting executed. So these were very, basic things, but it is very important to solidly understand these so that you can solve higher level questions very easily. So before we go ahead, I'll tell you one really important thing. Why do people use recursion? If they want, they can get things done without using recursion also, isn't it? They can execute their code using a stack, because anything that can be done using recursion can also be done using stack. You can create your own stack and you can simulate this behavior instead of calling the function again and again. But the reason for using recursion is, one of those is that your code is very simple, and whenever you see that, let's say you are at some particular stage 1, and from here, let's say you have got multiple choices. So I'm just trying to give an example. Let's say currently you are in India, okay, and you have to do your world tour. You want to tour the entire world. So you can start by going from India to Nepal, and you can also start by going from India to Sri Lanka. You can also start by going from India to Myanmar, and many other choices. So corresponding to different choices, there will be different kinds of experiences that you will have. There will be different kind of distances that you might cover, okay? So whenever situations are like this, that at a particular stage you have got multiple choices to make, now the thing is that when you make this choice, then you will go into this jungle. So the thing is, when you come back over here and you need to start from the next choice, you have to remember this, because how do you come back to this unless you remember this? So the way this is being remembered is by pushing these choices that you made in a stack. So if you see in a problem that at any stage you have got multiple choices and you have to execute that, then recursion can actually come in handy, okay? So I'll take a question to illustrate this, and that is a very basic question of recursion. So I'll be giving you a set, and how is it different from an array or something like that? It contains all the distinct elements. So all the elements of a set are going to be unique. There will be no duplicates. So the question is that I'll give you an array, and that array will represent a set. So by that I mean that the elements will all be distinct. So let's say array contains these elements 1, 2 and 3, okay? So these are the elements of my set, and that is the reason they are all unique. So now what I want to do is I want to print all subsets of this set. I want to print all subsets of this set. So can somebody tell me, if the set contains n elements, how many distinct subsets will be there? How many distinct subsets will be there? Okay, so 2 raised to power n is what I am hearing. So first thing to understand over here is that when I say print all the subsets, by default I mean print all the distinct subsets. Now what do I mean by distinct subsets? So if, let's say, there is a subset of this which contains 1 and 3, 1 and 3 is a subset of this, okay? So you cannot say that 3 comma 1 will be another subset. You cannot say that, because this 3 comma 1 is simply a permutation of this. Are you getting what I am trying to say? 3 comma 1 is just a permutation of 1 comma 3, okay? So these are repetitions over here. So basically here what I am interested in is all the different possible combinations. I am interested in all the different possible combination, and I am not interested in the multiple permutations of the same combination. Are you getting what I am trying to say? I am not interested in the multiple permutations of the same combination, okay? So think of it in this way, that if you remember, we had a lecture on permutation and combination where we discussed a bit about it. For any element, I have got two choices. If, let's say, I have to build a subset, okay, then for any element I have got two choices. And what are those two choices? Either I can take it or I can not take it, okay? So for this element I have two choices, for this element I have two choices, for this element I have two choices. So what will be the total number of combinations that I will get? It will be 2 into 2 into 2, so on till n. So it will be 2 raised to power n. So total number of subsets that I am going to get is 2 raised to power n. Now, is this guaranteed that all of these will be distinct subsets? The answer is yes, they will all be distinct subsets. And why they will all be distinct subsets, that also I will try to say. Because see, the moment you take a decision, let's say you said for 1 you had two choices, either to take 1 and then consider other numbers, or not to take 1 and then consider another numbers. So see, once you have chosen 1, then all the subsets that you will get by considering other numbers will all start with 1, isn't it? They will all start with 1. But if you have decided not to go with 1, then all the subsets that you will get will strictly not start with 1. Is that clear to everyone? So this being the reason, can it ever happen that there is a subset over here which was present over here also? Can it ever happen? This will never ever happen. So the point is, again I'll repeat the same thing which I had spoken while teaching permutation, that if for any element you have got m distinct choices and for the other you have got p distinct choices, then total number of combinations are m into p. And here they are distinct, because taking something is totally different from not taking it. That being the reason, there will be no duplications. Now one more thing to understand over here is that so this was my set and I wanted to print all the subsets. Yeah, so 2 raised to power n will be my answer. One more thing, since I said that subsets is all about considering all the combinations that are out there, okay? So combinations can be of different sizes, isn't it? So firstly, write down all the subsets of this. What subsets will it have? It will have 1, 1, 2, 1, 2, 3, 1, 3, 2, 2, 3, 3, and 1, 2, 3. And an empty one. 1, 2, 3, 4, 5, 6, 7. I think I maybe repeated something over here. Is there something that I repeated? Because I'm getting 1, 2, 3, 4, 5, 6, 7, 8, 9. What is it that I repeated? Can somebody see that thing that I have maybe repeated? 1, 2, 3, right? So I have repeated this 1, 2, 3. So you can see that I have got 8 different subsets of this set. Now the point I was coming to was subsets is all about combinations. Okay, so first thing, that how many combinations of size 0 you can get, or how many combinations of size 2 you can get. So if I have got n numbers, then how many combinations of size 2 are possible? It should be NC2. Do you remember that? It should be NC2. Okay. Similarly, how many combinations of size 3 will I get? It will be NC3. Okay. So do you understand over here that any combination in this will be different from any combination in this, because here there are 3 elements and here there are just 2 elements, and also within this combination there will be multiple combinations, and I am not interested in multiple permutations of those. Okay, so one way to conclude this answer is that, hey, there will be some subsets where 0 elements are there. So how many ways are there to select 0 elements from n elements? That is NC0. Now there will be some subsets where just 1 element is there. So number of ways to select 1 element out of n elements is NC1. Similarly, for 2 it is NC2, and so on till NCN, and this value also sums up to 2 raised to power n. Is that clear to everyone? So this entire thing also sums up to 2 raised to power n. Now you might see this thing very clearly, that there is just one subset of size 0 and there is just one subset of size n. Do you see that? The number of subsets of size r is equal to number of subsets of size n minus r. Do you see that? Number of subsets of size r is equals to number of subset of size n minus r. And why is that the case? Because do you remember this thing? NCr is equals to NC n minus r. Are you able to relate to this thing? So that being the reason this kind of thing is happening. So, and this NCr thing, it increases as r goes from 0 to n by 2, and then it decreases afterwards. Okay, so do you see that? Are you able to relate to this thing? I had spoken about this already. Okay, so these were few observations that I just wanted to discuss over here. Anyways, the original question was to print all these subsets. I want to print all these 2 raised to power n subsets of a given set containing n elements. So see, this is very, very important. And why will the recursion help? Because I already spoke that for any element there are multiple choices. That means that whenever I am at an element, I have got multiple choices, either to take it or to not take it. Okay, so let us see how recursion tree will look like. So one thing that all of you should get used to is creating this stack and then understanding the things is very, very complicated. So always convert your code into a recursion tree and just see how I am going to do that. See, this is my input array that contains 1, 2 and 3. Okay. Now what I am going to do is that since I have to print all these subsets, so I need a separate array. Okay, I need a separate array which will keep track of which elements I have selected so far. Okay, so I will call that as my temporary array. Okay, so I have a function. What it does, it takes in that temporary array which initially is empty, and it also takes in that which element I am considering right now. Okay, so I can start my journey from the left side of the array, which is element number 0. So I can start my journey from element number 0. See, this index I over here basically points to the element in my array. Now for any element, how many choices do I have? I have 2 choices. So the first choice was to not take it, and second choice was to take it. Okay, so if I do not take it, if I do not take this 0th element, which is 1, what will happen? Will this change? Will the temporary array change? No, this will not change. This will remain as it is. So you will move to the same temporary array. But since now you have made your decision for 0th element, you will move on to first element. Okay. But if you had chosen it, what would have happened? If you had chosen this 0th element, your temporary array would contain 1 and you would move to index number 1. Okay. Now, see, do you see over here that for index 0, which is for first element, you made the two choices that you could. Now, when this branch will explode, you will get all those subsets that do not start with 1 because you discarded 1. And when this will explode, you will get all those subsets that strictly start with 1 because you accepted 1. That being the reason, nothing over here will be equal to anything over here. Are you getting what I am trying to say? So this is the reason my approach would work. Whenever you make recursive calls, just see if something over here, can it come over here? If that can come, that means repetitions would happen. But if the choice is made in this way, wisely enough, then that repetition would not happen. Okay. Now, another thing, that at this level, which is level 0, I determined the fate of first element and I got 2 nodes. Now, at this level, which is level 1, you will determine the fate of this over here as well as over here. So you will get 4 nodes. At next level, 8 nodes. Eventually, at the last level, you will have 2 raised to power n nodes, which will be nothing but all the subsets. Are you getting what I am trying to say over here? That how this is going to look like? Okay, anyways, let's carry on. So now, element at index 1 is 2. So for this element also there are two choices, either do not take it or take it. So if I do not take this element, this temporary array will remain as it is. So it will remain as it is, and now I'll move on to the next index, which is index number 2. Okay, but had I taken this first element, my temporary array would look like this and I would move on to the next element. Okay. Now let's come over here. Now index is 2. Index 2 is element number, this element 3. So again here I have got 2 choices, either do not take it or take it. So if I do not take this 3, what will happen? This temporary array will remain as it is. Now I'll go to 3. Okay. But if let's say I had taken this, then in my temporary array I had 3 and I would move on to index number 3. Okay. What does this 3 signify? Can somebody tell me? This I signified index of the input. So when the value of I becomes n, where n is the size of array, what does that mean? That means that I am done with all the elements, isn't it? I am done with all the elements and now my journey is over. So basically this signifies an empty array. Why? Because now this has this started sliding and this has finished this up. That is the reason I came over 3. So now this is done. So should this be my termination condition? Yes. So whenever the value of I becomes equals to n, that means whatever is the current status of my temporary array, that is a consequence of the choices that I made. See, no, no, no. You said no for this, no for this, no for this. That is why you are empty. Look at this branch. No, no, yes. You said no, no, and then yes for this. That is the reason you just have 3. How many of you are getting what I am trying to say? So here you can print your another subset, which is just 3. Okay, cool. Now one more thing. The same thing would happen over here also. That here again you have got 2 choices, no and yes. So when you are at index number 2, which is 3, you have again got 2 choices, either to take it or to not take it. So if you do not take this 3, this 2 will remain as it is and you reached index 3, which is your termination condition. And if you had decided to choose this element at index 2, which is 3, you would have got 2 followed by 3 and you would move on to the index number 3. So this is also your termination condition. Now see, do you also see one important thing over here, that let us understand the physical significance of any function. See, these things that I am speaking over here will come in very handy when you study DP. These things are the states of any function call. Why? Because over the consequence of these calls, these two things are getting constantly modified, and they have got different values at different nodes. So they physically mean something. Now what is it that they mean? Like here they mean that if I just have one element which is from index 2 to 2, because if your index is 2, that means after 2 there is just one element. If I just have one element and currently I have 2 with me in temporary array, then how many different subsets can I make? The answer is 3. The answer is 2. Either you can bring 3 after this, or you cannot bring 3 after this. So if you bring 3 after this, you will get 2, 3, and if you do not bring 3 after this, you will just get 2. So this is what the physical significance of function is. The same thing, if you try to relate from here, no choice meant that, hey, all the subsets that this node will explode into will strictly not start with 1, and that is the reason. None of them is starting with 1. If you create the same decision branches over here, you will see that all of them start with 1. So like if you say a no and then a yes, so first index element is 2. If you do not take this, you will move on to index 2 and you will just have 1. And if you take this 2, you will move on to index 2 and you have 1 and 2. See, you understand this thing, no, that whenever you move down the level, you change your index from I to I plus 1. Why? Because now you have taken decision for that element. Whether you want to take it or not, you have taken the decision. Okay. Now again, when you are at 2, which is this, you have got two choices over here. Either you take it or you do not take it. So if you do not take it, what will happen? You move to 3 and this is just 1. And if you take it, you move to 3 and you will have 1 followed by 3. Similarly here also two choices, no and yes. 3, if you do not take this 3, you move to 3 and you just have 1, 2. And if you take this, had you taken this, it would have been 1, 2 and 3. So see, the entire game of recursion is about thinking of the choices that you have. And once you think about the choices, then you are able to think about how many parameters you need to pass. And then you can easily think, how do they change? When this is the decision, how do they change? When this is the decision, how do they change? If you can think these things, it's just a matter of converting it into lines of code and then the recursion is done. One more important thing, that these things are your termination condition. So you can easily trap your termination condition by checking the value of I. So whenever your I becomes equals to n, then you can say that, hey, I would want to terminate over here. Okay, so how many of you can write code for this? Let's say yes, those of you feel you can easily write the code for this. Okay, so let us say now I am willing to write the recursive code for this. So let us do that. So the function that I want to write would be a recursive function. First of all, let us develop a thought process, because I have seen people who after attending lectures are good at thinking but they fail to write the code. Okay, so let us do that together. I need to write a recursive code. So what kind of return value should it have? Does it need to return something, or can it just be a void function? What do you feel? I believe I can keep it void, because it needs not return something, it simply needs to print something. Okay, so I'll keep that as a void and I can name that function as print all subsets. Next thing is to determine what arguments will it take. So can somebody tell me what arguments does it need to take? What are the important arguments that it should have? See, input array can be global. Just for input array is not going to change. You see that? Input array is not going to change, so you can assume that is global, and even if you pass it, that is not going to change. You see that? So input array can be global. The size of input array can also be global. So let's say this was my input array of size n, which was happily global, okay? And I can pass it also. If I pass it, it is never going to change across the function calls. And this is the size. Okay, so first thing that I need is a temporary array. So I'll pass my temporary array by reference, because I don't want to create a new temporary array everywhere. That is not required. I can manipulate the same temporary array to get my job done, and we'll see how. Okay, apart from this temporary array, what is it that you need? You need an index I. This index I points to what? It points to the temporary array or points to the input array? What does it point to? It points to the input array and tells me that, hey, currently you have to decide the fate of ith element, whether you want to take it or you want to not take it. So I'll have an index I. Do I need something else than that? Anything else that I need? If by n you mean the size of array, then size of array is already there. Size of input array is already global. Index of temp array is another thing that you might want to need, and I will tell you why. See, the thing is that when recursive call flow happens, what happens? First function to be called is this, then this, then this, and then this. This is how the things happen, right? Now, when you insert into the temporary array, you need to know its size, isn't it? Are you getting what I'm trying to say? You need to know the size of temporary array, that how many elements it contains currently. Do you see that it contains different number of elements at different locations? Do you see that? It contains different number of elements at different locations. So how do I get to know that? If I have to, let's say a yes for element at index 1, which is 2, where should I put? For that, I need to know the size of this. If the size of this is s, then the new element should go at index number s. So that is the reason I need to keep track of it. So I would want to track the size of temporary array as well. So let me call this size s. And now I'll show you one very important thing. So generally people understand it. See, this is the difference between a good coder and somebody who just understands the logic and then leaves it as it is. In recursion, I would say that your assignments are of paramount importance. If you do that, if you really do that effectively, please rest assured that your life in all the other topics will be very, you would love those topics. So please code everything in recursion. Yeah, so what was I saying? That let us examine this thing very carefully. What is happening? That initially the size of this is 0. You said no, then you said no, then you said no. So this is empty over here, okay? And then when this had called this had returned. So now this will call yes branch. In the yes branch, you would want to take input of 2, okay? And now the size is 0, so you would place it at index number 0. So now you have a 3 over here, okay? So you printed this thing and then your job is over, okay? Now the control came over here, this is also over. So now the control came over here, now yes would trigger. So now again, do you see one thing, that here also the size of this thing was 0. So you placed at index 0 this value 3, and here also the size of this was 0. So you placed at index 0 value 2. So basically what happened, that the 3 which was over here, that got replaced by 2 over here. How many of you see that? This is the most important thing why I need to track the size. Okay, listen very carefully now. Likewise, you took this branch and this remained empty, okay? After this got invoked, the size of this was 0, so at index 0 you placed 3, right? Now when this is over, the control comes over here. This is also over, control comes over here. So now yes branch would trigger. When the yes branch triggers, what happens? this element which is input of 1 would be placed at index of 0, and previously at index of 0 what was there? 3. So now basically this 3 has been replaced by this 2. It has been overwritten by 2. Is that clear now? That this value 3 has been overwritten. And why and how have I been able to overwrite? I have been able to overwrite because I was tracking the size of temporary array using another variable s. That is the reason while I chose this yes path, when this entire thing was over, I placed this input of 1 at index 0 rather than placing it after 3 or something like that. So basically this size variable is very, very important because it will tell me at any point of time that how many elements of interest are there in my temporary array right now. By that I mean that how many elements have I consciously chosen in my decision path. So that is the main important thing over here, that you are using the same array and using the size of the array, size variable, you are overriding the elements, you are overwriting the value of the element at any position, and then you are printing those. So what is the first line of code that I should write in any recursive implementation? Recurrence relation, termination condition. How do I detect termination condition over here? What will be my termination condition? If my I has become equals to n, that is my termination condition. So what should I do? What should I do? I should print the contents of my temporary array. To print the contents of my temporary array, is it important for me to know the size of my temporary array? So what will I do? I can write a loop for j varying from 0 to size minus 1, simply cout temp of j. Okay, and then after printing any particular subset in a single line, you can give a new line, and then you basically want to terminate, so you can write a return semicolon. So this was your termination condition, where you printed the contents of temporary array and then you exited, right? But if this is not the case, that means you are at some non-terminal node. So when you are at some non-terminal node, what should you be doing? What should I do when I am at a non-terminal node? I have got two choices, right? The two choices are, either I can take the ith element with me, or I can not take this ith element with me. So let's say first branch that I take is to take it. So if I take this ith element, at which index should it go? Array of I should go into temp of what? It should go into temp of s. Is that clear? Why 0? S, right? It should go to temp of s. Is it necessary that your temporary array will always be empty whenever you are trying to place something? That is the reason you are saying 0, right? So it should be s. So you will do temp of s is equals to array of I, and after choosing this thing, now you can move down. So you can call this function again with the updated value of temp. What will be the value of I now? Whenever you move, the value of I becomes I plus 1. And what will be the value of size? Since you have chosen an element, the value of size will be size plus 1. Okay, so this was the call for inclusion, when I included array of I in my temporary array. If I don't wish to include it, then what should I do? If I don't wish to include it, I can simply keep my s as s. Are you getting that? If I don't wish to include it, my size will remain the same, and then at that size some other value will come and override it. So I'll call this thing with temp, change the value of I to I plus 1, and s remains as it is. This is how it happens. So see, using this variable s, I am very intelligently using the same temporary array, overriding the values at same index to different values at different recursive calls, and then printing out all the subsets. So how many of you understood this code? Just say yes, those of you got it. How is this working? So see, this is how your every recursive code will look like. So never mix your logic and code together. Whenever you have to think of a problem, and this is in general advice for all the problems, first think of the recursive logic, that how many choices do you have? Okay, repeat please after return. You will have to tell me what is it that after return, which thing you did not get, then I can repeat from there. Tell me this is that I got, and then I can maybe speak afterwards. Yeah, so I was saying that in any recursive problem that you get, you will have to first think of the logic, that how a particular problem is breaking down into smaller problems, and then what variables will be required, what will be the termination condition, and then only start writing the code. Why are you putting in S and not at 0? Okay, so this was the first question. Yatendra, what was your question? Let me answer both of them together. I got up to termination condition. Okay, anyways, so see, Priyam, in your temporary array, when you want to push input of I, are you pushing at index 0 or are you pushing at index 1? Where are you putting it? Where are you putting it? If your temporary array has 5 elements, the next element should obviously be the 6th one. Did you get it now? It's clear why I'm doing that? Okay, so Yatinder, just listen very quickly. This was very easy. Now here I said that whenever, let's say, I have to decide the fate of ith element, first choice is to take it and second choice is to not take it. So if I take it, that means I'll put this element after this in the temporary array. So I'll do temp of s equals to array of I. Is that clear? Is that clear why I have done this temp of s equals to array of I? After having done this, make the function call. So what is the function call? Pass the temporary array, increase the index. By increasing the index, what do I mean? That you have done whatever you wanted to do with input of I, now you will go to I plus 1. And since you have chosen this element, so you will do s plus 1. And this is your no branch. No branch means that you will go on to the next index, but you will not increment the size. This signifies that you are not considering the element to be inserted in your temporary array. Is that clear? Okay, cool. So what is passed as s in the initialization step? Yeah, who can tell me what should be the value of s in the initialization step? So when I call this function for the first time from my main function, my temporary array should be passed. The value of I should be 0 and the value of s should also be 0, because I do not have anything in my temporary array to start with. And the first element whose fate is to be decided is 0th element of my input. So the index I is also equals to 0. One more thing, when you declare this temporary array, what will be the size of this temporary array that you would want to take? Its size should be equal to the size of input itself, because the maximum it can grow is n. Maximum it would grow would be the size of set itself. Okay, so this is how you can easily get it done. Yeah, now, so do you see how many leaves are there? How many leaves are there in this binary tree? It is nothing but the number of subsets, which is 2 raised to power n. So let us first talk about the time complexity. What will be the time complexity of this recursive code? It will be approximately 2 raised to power n. And how can I logically explain that? First you can write this line as it is over here, and then these two things will remain as it is. Okay, because this simply says that you discard the ith element, you move to I plus 1th element with the same set of elements in your temporary array. And this simply says that at s index you have put array of I and you move on over here. So you can place no before this or you can place yes before this. Nothing much is going to change because you have a size variable with you, which actually gives you the fact that hey, elements from 0 to s in the temporary array are of my interest because I consciously chose just them. Okay, cool. So let us see how I can very effectively talk about the time complexity of this. See, in this binary tree that you can see, number of nodes here will be 2 raised to power n. How many number of nodes will be here? Above this, how many nodes will be there? So if in the last level 2 raised to power n nodes are there, before that number of nodes will be half of this. So number of nodes will be 2 raised to power n minus 1. Here 2 raised to power n minus 2 and here 1. So total number of nodes will be 1 plus 2 plus 4 till 2 raised to power n. Do you agree to this? This will be the total number of nodes, 2 raised to power n. And what is this sum? This is a GP, right? The sum of this GP will come out to be 2 raised to power n plus 1 minus 1. Okay. So I can say that effectively these many nodes are there. Okay. Now one more thing, that this is nothing but this is approximately order of 2 raised to power n only, isn't it? Approximately 2 raised to power n only, because in any perfect binary tree maximum number of nodes will be there at the last level only. Okay, and that will actually be equal to the sum of all the non-leaf nodes if you take a look over here. Okay, and in the termination condition the work that you do is printing. You print. So how many times at max this loop will run? N times if the size of your temporary array is n. So approximately you can say that your complexity is n multiplied by 2 raised to power n. So this is how you can comment on the complexity. Is that clear to everyone? That what will be the time complexity? 2 raised to power n nodes at the last level, which is maximum number of nodes at any level, and that multiplied by the time taken to print the temporary array, which could be order n if the size of temporary array is n, okay, at max. Okay, cool. So this was the recursive approach to solve this. Now, can I do this iteratively? Okay, so that is a very important trick and this will come very, very handy. See, the thing is that whenever you have got just two choices, then you can represent those choices in a bit. Are you getting what I am trying to say? Because a bit can either be on or off, which is true or false. You can say true means I included it, false means I did not include it. So let us take an example. If I say that no means 0 and yes means 1. So what will this extreme path look like? Extreme left path, which is n and n, what will this look like? If I replace n by 0 and yes by 1, so this will all be 0, 0, 0. What will this be? No, no, yes. What will this be? 0, 0, 1. What will this be? 0, 1, 0. What will this be? 0, 1, 1. Are you seeing how these things are being made? And what will be the rightmost path where all are yes? That will be 1, 1, 1, right? This is a binary representation of 0. This is a binary representation of 1. This is a binary representation of 2. This is a binary representation of 3. And this is a binary representation of 2 raised to power n minus 1. How many of you are able to understand what I have done over here? So what you can do is, you can consider numbers from 0 to 2 raised to power n minus 1, and you can create binary representation of that number. Once you have created that binary representation, then the bits that are on, just select those numbers from the input and print those. That will denote a unique subset. How many of you understood this? Say yes, those of you got it. So this approach is also called as bit masking. Okay. Repeat selection method. So if let's say you have 0, 1, 1, what does that mean? 0, 1, 1 means what? That you selected element at index 1 and element at index 2, isn't it? You write the binary representation of numbers from 0 to 2 raised to power n minus 1. When you have chosen a particular num between this and written its binary representation, then simply pick the elements whose indices have these on bits in the input and print those. Did you get it now? Is it clear now? So this can be an easy enough approach. This is also called as bit masking, wherein you hide your information in a bit. Mask means to hide. So you take a bit and you hide your, why do you need me to write a pseudocode over here? Is that is very, very easy, right? Like, what is it that you have to do? You have to write a for loop from 0 to 2 raised to power n minus 1. Now for any particular value I that lies in between 0 to 2 raised to power n minus 1, write its binary representation. You know how to write binary representation? I believe you should be able to do that. And once you have written that binary representation, then those bits which are on, select those elements from your input and print those out. Did you get it? Can you try that out on your own now? If you are having a doubt writing the code, that means you did not understand the logic. Because if you understood the logic, then this is a very straightforward thing to do. Okay, cool. So this was another approach that you have. It will again have the same time complexity, order 2 raised to power n multiplied by n, because you will have to consider the input array and select the elements and print those out. And what about space complexity? Think what will be the space complexity. What is the extra space that you are using over here? You are not using any okay, first talk about the space complexity of recursive approach. What will be the space complexity in this recursive approach? Order n, and where from that order n comes? Is that the size of temporary array that I am using? Yes, the answer is yes. N is the size of temporary array that I am using. Apart from that, anything else? Yes. What is that something else? The maximum height of my recursion tree or my recursion stack will be how much? It will be n. In fact, any root to leaf path that you see over here will be of size n. So order n plus n is almost order 2n. Okay. Now in the other approach, recursion stack will not get created, but when you want to pick the elements, okay, and print them out, so before that you store the binary representations somewhere. Okay, so when you store if you store the binary representation, then you might need some extra array, but you can do it without storing that binary representation also. Won't we have log n for masking in the iterative approach? Yeah, right. You will have log n time will be consumed to get the binary representation of a number n out. But apart from that, as I said, that in the worst case it could be that all the bits are going to be on, okay, and in that case you would print out all the elements. So it would be taking order n time to print out the elements over there. You see over here, right, the highest number that you would get will be 2 raised to power n. And what will be log 2 raised to power n base 2? It will be n, right? So order n time will be taken to get the binary representation of that out. So I will put this question in your assignment, and now we will move on to another question, and we will see that how thinking in exactly the same way can help us solve the problems. See, if at any point of time you feel that you yourself are not able to think, or you are thinking this way but I am speaking that way, so you can let me know, because the most important thing over here is to think recursively and recursively.